All right, so we're going to prove the unique circle theorem, which states that there is exactly one circle through any given three noncollinear points. So, through any three noncollinear points, we can always draw a circle. So first, I'm going to draw the circle, but then I'm going to prove why it is, in fact, that we can draw a unique circle with any three given points. So, here is our circle. As you can see, I was able to fit all 3 points within the circle. But let's go ahead and prove why we were able to do that. So, proof, since the points are non-collinear, we can draw two segments, right? Two segments, AB and AC. All right, so let's go ahead and draw those. We're going to, of course, for any segment, there exists a perpendicular bisector. So we're going to let B and C be the perpendicular bisectors of, let's see, B would go with AB and AC respectively. All right, so let's go ahead and draw those perpendicular bisectors. So I'll do the best I can. All right, so I drew the perpendicular bisectors. So here, right there, and right there. And of course, this is congruent to that. And this will be congruent to this, right? So, of course, since A, B, C are noncollinear points, then we know the perpendicular bisectors of these segments will eventually touch each other because they won't be parallel. So, let's go ahead and since A, B, and C are non-collinear, this implies that B is not parallel to C, which implies B will intersect C, right? Okay, so since they will intersect eventually, we're going to let P be where B intersects C, right? So we can see down here, this point of intersection is going to be P. Okay? So since P lies on the perpendicular bisector of AB, this implies by the perpendicular bisector theorem, right, that AP is going to be congruent to BP, right? So let's go ahead and draw those segments. So AP is going to be congruent to BP, right? Similarly, since P lies on the perpendicular bisector of AC, this implies by the perpendicular bisector theorem that AP will be congruent to CP. So let me go ahead and draw that here. All right, so that means that all three of these, right, are congruent. So we have BP is going to be congruent to AP, and AP is congruent to CP, this implies that BP is equal to AP, which is equal to CP, and rightfully so, we're going to give all these a measure of R, right? AKA for radius, right? So we'll go ahead and do, instead of those 3 lines, we'll do R, right? All right, so R, R, R. Since A, B, and C are equidistant from point P, right? This implies that A, B, and C they are elements of circle P, right? By definition of a circle, if these 3 points are equidistant from a point P, that means they lie on the circle P. All right, so at least we've proven that A, B, and C do lie on a circle P from this perpendicular bisector argument, right? Now all we have to show is that this circle P is actually unique. Okay, so suppose there exists a circle Q where A, B, and C lie on that circle Q, right? These same points from above, right? So here's our circle Q. As you can see, it's the same as this above, but I put the Q because with a uniqueness argument, we're basically going to show that Q must be the same point as P, right? But here is our argument. So if A, B, and C lie on circle Q, this implies that A, B, and C are equidistant from this point Q, right? So of course, this implies that AQ is congruent to BQ, which is going to be, which is congruent to CQ, right? Okay, so since AQ is congruent to BQ, right? This implies by the perpendicular bisector theorem that Q lies on the perpendicular bisector of AB, right? So AKA, this means that Q is on line B, right? Similarly, since, what is it? AQ is congruent to CQ, right? Since AQ is congruent to CQ, this implies by the perpendicular bisector theorem that Q lies on the perpendicular bisector of AC, right? AKA, we know that Q is an element of C. So since Q is an element of B and Q is an element of C, this implies, this is the point, so Q is the point of intersection of line B and line C, right? These perpendicular bisectors. And since B is not parallel to C, right? this implies that they only intersect at one point, right? B intersects C at one point. And remember, above, we showed that these perpendicular bisectors intersect at P, and down here, we show that they both intersect at Q, but since they're not parallel, they only intersect at one point. So this implies that P must be the same point as Q, right? So not only have we proved that for any three non-collinear points, we can draw a circle through those 3 points, we've also shown that the circle that we draw through those 3 non-collinear points will also be a unique circle. And that is the proof to our theorem.